Good morning. I would like to present on a new specification for multi-wavelength optical laser sources for advanced integrated optics. My name is Chris Cole. I'm the chair of the CW-WDM MSA, which authored the standard. And I would like to kindly thank the organizers of Market Focus. It's really a great forum. So I'm appreciative of being able to contribute to it. So let's ask ourselves, why do we need a new, in particular, high count WDM datacom standard? Let's review the history of datacom, in particular, Ethernet optics. Up to 10 gigabit Ethernet, the dominant paradigm was one wavelength NRZ. 40 and 100 gig shifted to four wavelengths, CW-WDM 4 NRZ, and 200, 400, and likely 800 gig will be four wavelength PAM4. If we go beyond that and insist on a four wavelength paradigm, let's say because the end users like CW-WDM 4, if we choose to use IMDD PAM4, we have to go to a 200 gigabaud rate, which may not be feasible in the time frame of interest of 1.6 tera transceivers. Alternately, we could move to coherent, which a number of people are advocating, and that certainly is feasible, although in terms of cost, size, and power, I think there's some serious questions whether that would work in the data center. Alternately, if we're willing to move away from the four wavelength paradigm, our choices for IMDD become a lot more palatable. We could do 50 gigabaud PAM4 or 100 gigabaud NRZ, both of which are going to be very feasible when we're considering 1.6 tera. So what high count WDM provides is an alternative to higher order modulation and its associated complexity. Let's also look at modulation choices, and in particular, turn to Shannon for guidance. Here's Shannon's capacity theorem. It states that the theoretical capacity limit is the bandwidth times log 2 of 1 plus the signal to noise ratio. So now if we look at the channels of interest in optical datacom, in blue, we have the single mode client channel, which is, this is shown in electrical dB loss to be able to compare it to the copper channel. We see that for the frequencies of interest for data signaling, it's basically flat. In contrast, the copper channel, which is what connects an ASIC to the optics, has dramatic roll-off. Here it's linear on a y-axis log scale. If it was on a linear scale, it'd be falling off exponentially. We're also showing the signal-to-noise ratio of a single-mode transceiver, shown here in blue as well. We can see it's quite modest. And the copper SerDes, which is on ASICs or PHYs, has a fairly substantial signal-to-noise ratio. Both of these are back-to-back, no-FEC typical numbers. So now what the guidance tells us is that for the high bandwidth, low signal-to-noise application, which is the optics, we should use the lowest modulation order and just take advantage of the high bandwidth, so NRZ. And for the SerDes channel with low bandwidth but high signal-to-noise ratio, we can take advantage of that signal-to-noise to increase the modulation order. And this is from a presentation I gave in 2015 at the tail end of the IEEE optical modulation debate. Here's another way to look at the SNR advantage of NRZ over PAM4. This is expressed in vertical eye closure penalty. This is plotted versus alpha, which is the bandwidth over the bit rate, that ratio. And what we see that at the beginning of technology, when the bandwidth is limited, PAM4 and NRZ have similar eye closure, but as the technology improves, the bandwidth goes up, and then NRZ quickly gains about a 3 dB advantage. This includes an offset for the differences in the noise filtering. The other way to view this is that the x-axis is a function of time. So over time, NRZ gains a 3 dB advantage. So why PAM4 optics? Well, 50G PAM4 was adopted for ASIC SerDes, 50G copper lanes. This is between the ASIC and the module, as well as others in 2012. As we saw earlier, that's a sensible decision. That's what Shannon would suggest we do. But 3 years later, PAM4 was also adopted for optics, which is not, technically the best long-term solution. Why was that? Well, it enabled reuse of 50G PAM4 SerDes technology and reduced the cost and time to market of initial shipments by taking advantage of existing optical packaging and optical components. Predictably, optical component bandwidth increased. 50 gigabaud technology is now mature in shipping and volume. But the PAM4 3BD SNR power and cost penalty is permanently locked in. Nevertheless, PAM4 optics technology remains the best choice for Ethernet, exactly because it is part of an ecosystem. However, emerging applications with their own ecosystem can consider alternatives like high count WDM. They're free to optimize their technical solutions. And this is where the CW-WDM MSA comes in. Its objective is to develop high count WDM laser source specs for emerging applications. Note that it does not include writing a link specification. That is left up to the users. It was formed in April 2020. The website is listed here. I'm the chair. Matt Sisek is the editor, and we have 2 associate editors, John Johnson and David Lewis, and Christine Rabe is taking care of marketing for us. We published the Rev 1.0 spec several months ago, and we have 11 promoter members and 36 observer members. Here are the promoter members. I'm not going to go through all of them. This is all available on the website. You're welcome to peruse. In fact, I encourage you to do that. And here are the 36 observer members. The MSA defines 3 spans for the various grid alternatives. The widest span is 36 nanometers. It allows 8 wavelengths on an 800 gigahertz grid, plus 1 wavelength, which is optional. You'll see that for all the wavelengths. This is an old concept that when you have a high number of channels, the overhead for having a dedicated channel for synchronization, clocking, whatever, is quite reasonable because it's divided among many channels. So that's how many interfaces used to be designed. And now that we're coming back to many channels again, this is something that can be considered. The 800 gigahertz grid is the same grid as used by 400 gigabit LR8, LWDM. It's an 800 gigahertz grid. We can see there's an overlap between a number of wavelengths. Remember, the dominant grid for datacom is CW-WDM4. That's shown here on the first line. You can see it's got a fairly wide span, 80 nanometers, with it's a 7 nanometer range over temperature here. We've also shown how these MSA grids fit into a PDFA gain profile. This is a typical 3 dB bandwidth. PDFA is analogous to EDFA and C-band. and allows you high quality amplification, either for laboratory or field use. If we go from the 800 gigahertz grid with which we're familiar because it's actually deployed to a 400 gigahertz grid, we are now doubling the number of data wavelengths to 16. And if we cut the spacing to 200 gigahertz, we're doubling the number of wavelengths to 32. The second span set is 18 nanometers. We now have, using 400 gigahertz spacing, 8 data carrying wavelengths. With a 200 gigahertz grid, we have 16, and with a 100 gigahertz grid, we have 32. And then again, you can see the additional single wavelength for synchronization. For the 18 nanometers, we can see it fits in very nicely in the 3 dB bandwidth profile of a PDFA. And it overlaps in terms of the span with LR4, 100G LR4 and 200G LR4 LWDM grid, which is 4 wavelengths on an 800 gigahertz spacing. The final span for possible wavelengths is 9 nanometers. There are 2 choices now on a 200 gigahertz grid. There are 8 wavelengths, and a 100 gigahertz grid gives us 16 wavelengths. So that's just a subset of the 18 nanometers. And again, we see very strong overlap with LR4 and PDFA gain profile. There's many other specifications. Again, I encourage you to go to the website, which has the spec published. I'll only give you a couple of key specs so you get a sense for how the laser sources are defined. They're written in terms of power limits per fiber, so you sum the power and all the wavelengths. Type 1 is right at the eye safety limit. So 18 and 36 nanometer are right at the eye safety limit. Then the 9 nanometer span could have been higher, but we chose to keep it same as 18 nanometers as a subset. Type 2 is the eye safety limit reduced by 6 dB. So this would be for low power applications where the link budget wasn't critical, but minimizing the energy use was. And then the type 3 is the eye safety limit plus 6 dB, where we're trying to maximize the link power. In this case, special precautions would have to be taken with the source. For example, it would be mounted on the same card so that actually the fiber is not exposed to service personnel. The other important spec is the wavelength accuracy. There are 2 types again. One is where the center wavelength offset and variation are multiples of grid spacing, and the type 2 where they're a fraction of the grid spacing. So the type 1 is very benign in terms of requirements on the source, but it now forces the transmitter and receiver to actively track the laser. We see plus minus 5 nanometers for the initial center wavelength offset, and then another 4 nanometers of drift is allowed. Type 2 is considerably more stringent. It makes the laser source tougher because now it has to hold the initial offset to 0.5 nanometers and the variation to another 0.5. But now the transmitter and receiver have a pretty good idea where the wavelengths are. And so wide tracking is not required. There's a associated development. I'm sharing this with you to show you that there are many people looking at high wavelength count, O-band, datacom-like applications. ITUT study group 15 Q6 is working on standardizing a 12 wavelength O-band mobile standard. It's called CW-WDM. And as everyone knows, mobile is very cost sensitive and it has its own ecosystem. So it has the luxury to define an optimized solution. They recognize that low modulation order leads to lowest power, lowest cost. And so instead of increasing modulation or from previous solutions, they're going to more wavelengths or considering that. Nevertheless, they're still leveraging the high volume lasers used in the IEEE for LWDM and CW-WDM optics. The spans overlap those two. One of the main proposals is 800 gigahertz space, 12 wavelengths. This is common with the CW-WDM MSA, 36 nanometer span, 800 gigahertz space wavelengths. And it's also common with the LR4 and LR8 grids that the IEEE used. Now, the major issue for 800 gigahertz spacing, 12 wavelength solution is 4-wave mixing penalty. The MSA, CW-WDM MSA, had studied this and considered it, and Associate Editor John Johnson presented extensive analysis of 4-wave mixing penalty in support of the Rev 1.0 spec. He presented more extensive analysis of 4-wave mixing more recently in Q6 in support of the CW-WDM standardization effort. Week ago, Q6 has provisionally decided to use 800 gigahertz for the 4-kilometer application code. A lot of work is still left to be done. The 4-wave mixing penalty for the stringent application may be found too hard to meet, although we're optimistic. But if that happens, then a wider space 12 wavelength WDM proposal will be considered. So again, important development. We're supporting it, watching it very closely, and we will be having a liaison activity with the ITUT to mutually advance application of high count O-band WDM. So what is our current status? As discussed, the Rev 1.0 specification is published. I gave you the highlights, obviously more details there. Please go to the website. It's a public document. It provides the framework for high count WDM laser sources. It isn't a complete spec. You can't just take that document and go to a supplier and say, give me a laser source. You're going to have to do more work. But that makes sense because we don't specify link parameters. So initially, we think these applications will be bookended. They'll be proprietary, and so additional specifications will come from these applications for the laser sources. And that's what the next step is for the industry to develop products using the MSA framework specification. We don't know enough right now, or don't presume to guess what the applications are. There are many applications which are published as references on our website, but we don't really want to be picking them. We will promote the standard and facilitate industry collaboration, but we'll leave it to the market to select successful solutions. Now, once successful solutions develop in the market, especially multi-vendor solutions or high-volume solutions, the MSA will then consider standardizing them to further support the growth. And I thank you very much for your attention.